Hello friends, welcome to this YouTube channel. Today we are going to solve one numerical problem on three-phase medium length transmission line. By solving this problem, we shall learn how to determine percentage voltage regulation and efficiency of transmission of a three-phase medium length transmission line using its nominal T equivalent circuit when load details and values of transmission line parameters are given. Using nominal T method, we have to calculate the sending end voltage, the efficiency of transmission, and the percentage voltage regulation of a three-phase 50 Hz 100 km long transmission line supplying a load of 20 megawatts at 0.8 power factor lagging at 66 kilovolts. The resistance per phase equals to 10 ohm, inductance per phase equals to 111.7 millihenry and capacitance per phase equals to 0.9954 microfarad. Let us first write down the given data. Load PL equals to 20 megawatts, that is equal to 20 into 10 to the power 6 watts. Line to line receiving end voltage VR line equals to 66 kilovolts, that is equal to 66,000 volts. For star connected system, receiving end voltage per phase VR equals to VR line divided by root 3, that is equal to 66,000 divided by root 3, that gives us 38,105 volts. Given load power factor cos phi L equals to 0.8 lagging. Let us now calculate power factor angle. Phi L equals to cos inverse 0.8, that is equal to 36.8699 degree. We know that power consumed by the load PL equals to root 3 times VR line into IL cos phi L. Therefore, load current IL equals to PL divided by root 3 times VR line into cos phi L. Using values we get 20 into 10 to the power 6 divided by root 3 into 66,000 into 0.8, that gives us 218.7 ampere. Load current may be expressed in polar form as IL equals to IL at an angle minus phi L, that is equal to 218.7 ampere at an angle minus 36.8699 degree. Given supply frequency F equals to 50 Hz, resistance per phase R equals to 10 ohm, inductance per phase L equals to 111.7 millihenry, that is equal to 111.7 into 10 to the power minus 3 Henry. Capacitance per phase C equals to 0.9954 microfarad, that is equal to 0.9954 into 10 to the power minus 6 farad. Let us now determine inductive reactance per phase. XL equals to 2 pi F into L. Using values we get 2 pi into 50 into 111.7 into 10 to the power minus 3, that gives us 35.1 ohm. Capacitive susceptance per phase Vc equals to 2 pi F into C. Using values we get 2 pi into 50 into 0.9954 into 10 to the power minus 6, that gives us 312.7 into 10 to the power minus 6 mho. Transmission line impedance per phase Z equals to R plus JXL, that is equal to 10 plus J 35.1 ohm. Now we shall determine per phase impedance of half of the transmission line. ZH equals to half of Z, that is equal to 5 plus J times 17.55 ohm. This may be expressed in polar form as 18.248 ohm at an angle 74.1 degree. Taking receiving end voltage per phase as reference, we can write VR equals to 38,105 volts at an angle 0 degree. We have obtained load current IL equals to 218.7 ampere at an angle minus 36.8699 degree. This may be written in Cartesian form as 174.96 minus J times 131.22 ampere. Per phase impedance of half of the transmission line ZH equals to 18.248 ohm at an angle 74.1 degree, and capacitive susceptance per phase BC equals to 312.7 into 10 to the power minus 6 mho. Let us now calculate capacitor voltage per phase. Vc equals to VR plus IL into ZH. Using values we get 38,105 at an angle 0 degree plus 218.7 at an angle minus 36.8699 degree into 18.248 at an angle 74.1 degree. That gives us 41,282.5535 plus J times 2,414.5265 volt. This may be written in polar form as 41,353.1 volt at an angle 3.3473 degree. Now we shall calculate capacitor charging current. IC equals to Vc into J times Vc. Using values we get 41,353.1 at an angle 3.3473 degree into 312.7 into 10 to the power minus 6 at an angle 90 degree. That gives us 12.931 ampere at an angle 93.3473 degree. This may be written in Cartesian form as minus 0.755 plus J times 12.91 ampere. Now we shall compute sending end current. Is equals to Ic plus IL. Using values we get 174.205 minus J times 118.31 ampere. This may be expressed in polar form as 210.582 ampere at an angle minus 34.1821 degree. Let us now determine sending end voltage per phase. Vs equals to Vc plus Is into ZH. Using values we get 41,282.5535 plus J times 2,414.5265 plus 210.582 at an angle minus 34.1821 degree into 18.248 at an angle 74.1 degree. That gives us 44,229.7688 plus J times 4,880.3459 volt. This may be written in polar form as 44,498 volts at an angle 6.297 degree. We have obtained sending end voltage per phase Vs equals to Vs at an angle delta equals to 44,498 volts at an angle 6.297 degree, and sending end current Is equals to Is at an angle minus phi 1 equals to 210.582 ampere at an angle minus 34.1821 degree. For star connected system, line to line sending end voltage Vs line equals to root 3 times Vs, that is equal to root 3 into 44,498, that gives us 77.073 into 10 to the power 3 volt or 77.073 kilovolt. Phase difference between Vs and Is, phi s equals to delta plus phi 1. Using values we get 6.297 degree plus 34.1821 degree. That gives us 40.4791 degree. Now we shall calculate sending end power factor. Cos phi s equals to cos of 40.4791 degree. That gives us 0.7606 lagging. Now we shall compute sending end input power. Ps equals to 3 times Vs into Is cos phi s. Using values we get 3 into 44,498 into 210.582 into 0.7606. That gives us 21.38 into 10 to the power 6 watt or 21.38 megawatt. Now we shall compute efficiency of transmission. Eta T equals to PL divided by PS. Given power delivered to the load, PL equals to 20 megawatts. Therefore, eta T equals to 20 divided by 21.38, that gives us 0.9355 per unit or 93.55%. Now we shall remove the load from the receiving end and calculate no load capacitor charging current. ICO equals to Vs divided by ZH minus JXC. We have obtained sending end voltage per phase Vs equals to 44,498 volts at an angle 6.3 degree. Per phase impedance of half of the transmission line ZH equals to 5 plus J times 17.55 ohm, and capacitive susceptance per phase BC equals to 312.7 into 10 to the power minus 6 mho. Now we shall calculate capacitive reactance per phase. XC equals to 1 upon BC, that is equal to 1 upon 312.7 into 10 to the power minus 6, that gives us 3197.95 ohm. Let us now determine ZH minus J times XC, that is equal to 5 minus J times 3180.4 ohm. This may be expressed in polar form as 3100 80.404 ohm at an angle minus 89.9 degree. Using values we get ICO equals to 44,498 at an angle 6.3 degree divided by 3100 80.404 at an angle minus 89.9 degree. That gives us 13.9913 ampere at an angle 96.2 degree. We have obtained capacitive reactance per phase Xc equals to 3197.95 ohm and no load capacitor charging current ICO equals to 13.9913 ampere at an angle 96.2 degree. Now we shall calculate no load receiving end voltage per phase VRO equals to ICO into minus of J times Xc. Using values we get 13.9913 at an angle 96.2 degree into 3197.95 at an angle minus 90 degree. That gives us 44,743.5 volt at an angle 6.2 degree. Let us now determine voltage regulation, that is equal to VRO minus VR divided by VR. We have obtained receiving end voltage per phase on load VR equals to 38,105 volts. Therefore, voltage regulation equals to 44,743.5 minus 38,105 divided by 38,105. That gives us 0.1742 per unit or 17.42%. So today we have solved one numerical problem on three-phase medium length transmission line. By solving this problem, we have learned how to determine percentage voltage regulation and efficiency of transmission of a three-phase medium length transmission line using its nominality equivalent circuit when load details and values of transmission line parameters are given. Hope this lecture has been useful for you. If you have any suggestion or question, please drop it in the comment section below. If you have liked this video, give it a thumbs up and share it with your friends. Thank you.